Okay. All right, is that it?
Yes.
Okay. So it's a pleasure to see all of you. And I understand that you have this meeting, which is mainly concerned with nanoscience, nanotechnology, that I would like to put this in a broader perspective. First of all, welcome everybody. It's all these faces from around the world, far up from here. And I would like to give you my best greetings from France and from Strasbourg and from ISIS in Strasbourg, where Manuel has worked for some time. So, as you see, the title of my lecture has to do with nanoscience and nanotechnology, and with a specific approach which we have been pursuing, self-organization. And I will try to give you a sort of a broad outline, a perspective about the field, but not just the field of nanotechnology, also put it into a broad perspective. As you know, 2011 is the International Year of Chemistry, so it's also a time where you can think in somewhat broader terms about what chemistry is and what chemistry is bringing to the sciences in general. So we can think about what would be the big question to ask. When I say the big question, ask not only to chemistry, but to science in general. What is it? The big question is, how does matter become complex? What I mean by this is how the evolution of the universe has been evolving from the elementary particle to the thinking organism. And maybe there are even higher forms of complex matter that might be at some stage in the future be created. So, what is chemistry contributing to this big question? This question has to do with how did the universe generate complex organisms like human beings? And as you may know, physics deals with the laws of the universe, a very big problem. How does the universe function? What are the basic laws of the universe? Biology deals with the rules of life, also a very big problem. How do living organisms, and even more so thinking organisms, function? And chemistry is building the bridge between the two. Chemistry can provide the means for understanding how from general laws you can come to specific expressions of these laws, like a thinking organism on the planet Earth, knowing that probably on other planets there are other thinking organisms somewhere in this universe. So, if we consider then how chemistry has evolved and how chemistry can progressively contribute to give an answer to that question, what would be that answer? The answer to that question, in fact, we know the name by which we can designate it. There is a name which describes the answer, and this is the name which deals with the path from this divided matter to condensed matter, organized matter, living matter, and thinking matter. And this is self-organization. I mean by this that it has happened by itself on the basis of the laws of the universe, of our universe. And these laws are such that one can consider even self-organization to be a sort of a cosmic imperative. Here again, I mean that the universe as it is built, our universe as it is built, will lead in a sort of an almost obligatory fashion to organization. Now, this is the big picture. And this is a big picture which is valid for physics, for biology, and for chemistry. So how has chemistry started to contribute to that? Of course, the beginning of chemistry was to understand what pieces make up matter. And these are the elements. So using the atoms, which characterize the elements, one can think of building molecules, and in this way, molecular chemistry developed. It developed by trying to understand how one can link atoms to make molecules by these bonds all of you know are called covalent bonds. Trying to master how to break bonds, how to make bonds, and how to construct very efficiently, very selectively, highly complex molecules. Two milestones along the way can be cited. In 1828, a German chemist, Friedrich Wöhler, synthesized urea, a simple molecule. It is a simple molecule, but it was quite an achievement at that time because Wöhler made urea, which can be considered as an organic molecule, from a non-organic molecule entity, a salt, ammonium cyanate. And in doing so, he built up a new entity, urea, contained in living organisms from a compound which was an inorganic, a mineral, so to say. Now, 150 years later or so, the synthesis of vitamin B12, you can see, realized a very complex molecule, much more complex, of course, than urea, which has very few atoms. Here, many atoms are there, and the construction, the synthesis of this molecule has taken about 12 years and has involved about 10 to 12 to 15 people per year. So you can see it was an immense effort to build it up. But it also showed that this was done by two groups, Robert Woodward at Harvard and the group of Albert Eschenmoser in Switzerland at the Polytechnical School in Zurich. I myself worked with Woodward for a year, and I made this part of the molecule here. So you can see that over these 150 years, molecular chemistry has really become a very advanced chemistry, making many progresses in how to connect atoms, how to construct very complex entities. And of course, this has continued since the 70s of last century, since 1970, and so it has become further advanced and has developed new methods, new compounds, new properties, and this will of course continue still for many, many years. Molecular chemistry is not finished, by far not. However, we can ask a question at this stage. We can ask, we know about molecules. What do we know about the world beyond molecules? And let me introduce this by two pictures. Here you see a blue sphere, which is a cancer cell, and two colored bodies, these purple colored bodies, which are killer cells. These killer cells in our own organism have the mission to find the cancer cell and to destroy it. So the question you can ask, how do the killer cells know that the object they attach to is a cancer cell and not a normal, healthy cell? They are not allowed to make mistakes. If not, you have a big problem. In the same way, this is a white blood cell which has been artificially colored in red with blue dots. The blue dots are particles of the HIV virus. When this virus hits this cell, white blood cell, it can penetrate it. How does the virus know that it has now reached the target and can invade the cell? Something must tell the virus that the target has been reached and now I can invade. Obviously, this cells, this virus, they all are made of molecules. And when they touch each other, it's the molecules in their surface, on their surface, which touch each other at the interface between the red blood, between the cancer cell and the killer cells, or at the interface between the white blood cell and the virus. So the molecules which constitute these, which constitute the membrane and which are located in the membrane of these cells, they touch each other. And in doing so, this interaction informs the cells about the other partner. So what does that mean? This means that molecular chemistry, which deals with molecules made from atoms, has another step to go towards what we call supramolecular chemistry, which is the chemistry of entities which lie beyond the molecule, where the molecules interact with one another, and where, like in the recognition between the membranes, between the molecules in the membranes of the cancer cell and the killer cell, or the white blood cell and the virus, these interactions inform one of the objects about what the other one is. Now, these interactions depend on non-covalent bonds, bonds which exist between molecular entities once the covalent bonds are saturated, and this led to the development of a chemistry of molecular assemblies of what do molecules do when they get together and when they interact. 3 functions have been studied over the last 40 to 50 years. How do molecules recognize each other? How can they react on each other? And how can they transport, that means carry, one another through a barrier, like a cell membrane, a natural membrane, or an artificial membrane of a liposome, for instance. So chemistry, to sort of give a general panorama, has first been a molecular chemistry. Using molecular chemistry and organic synthesis, using covalent bonds, one can design what one may call receptor molecules which bind substrates. These two interact by non-covalent interactions, non-covalent forces, and lead to supramolecular entities. And these entities can recognize each other, can transform, react with each other, and can help each other to cross barriers. On the basis of this, as we will see a little bit later, self-assembly and self-organization can occur, which, when it deals with functional components, leads to functional systems, functional devices. So that is the panorama. Now let's look more closely. First of all, what is molecular recognition? Molecular recognition is the way in which molecules selectively attach to one another. This requires, first of all, interaction forces for binding. Without interaction forces, without non-covalent interaction forces, you have no binding, so you need this. But this is not enough. In order to recognize, you have to have information. So information is required for selective interactions between molecules. Without information, there is no selectivity. Therefore, molecular recognition clearly shows that chemistry deals also with information. And this information can be described by a double complementarity in shapes and sizes, that means geometrical complementarity, but also a complementarity in interactions, meaning by that, for instance, plus attracts minus, minus repels minus, and so on, dipoles align, and a lot of many other interactions. A very simple picture of this recognition has been given already in 1894 by a German chemist, Emil Fischer, when, and that year, in a very famous paper, he said that in order for an enzyme to act on its substrate, they have to fit together like Schloss and Schlüssel, like a lock and a key. These geometric objects shown here on the left. And this is, of course, a very simple picture, but it's a very good image which represents the basis of recognition. Of course, we now know that there can be adjustment between the lock and the key, but basically the image is good. So, once we know better about supramolecular chemistry, we then have to try to see if we cannot use this knowledge in the following way. In order to understand recognition, one can pre-organize matter. I mean by that, building chemical locks for chemical keys, molecular locks for molecular keys, or the reverse. Once you understand that better, you can think of using this knowledge in order to try to set up systems which will spontaneously, but in a molecular recognition directed way, generate more complex architectures. In other words, you want to generate supramolecular architectures using molecular recognition features in a spontaneous way, but controlled by these molecular recognition patterns. So let's have a look at some very specific species-specific examples which deal, I have chosen it in this way, also with nanoscience and nanotechnology. First of all, in order to make you understand how this recognition, this self-organization functions, let's take a biological example. The tobacco mosaic virus is a rather large polymolecular entity, which is shown here, built up from this piece of cake, which goes together and progressively generates the final entity, 2,130 protein subunits, or such subunits, plus the genome of the virus, one molecule of viral RNA, get together and spontaneously generate this entity, which is here described in somewhat better detail by the result, the crystal structure, and the entities here shown here. These are these 2,130 protein units. Now this looks like magic, but it is not magic. It's simple chemistry. It is organic chemistry. Each of those pieces of these components has a given shape, and on the surface of these components there are interactions such that they bind together in a very specific way, totally directed by the non-covalent interactions occurring between the surfaces. So it looks complicated. It is complicated, but it is not a complex case because each of these pieces has the information necessary for specifically connecting to the other one, interacting with the other one in a supramolecular way, and then quite normally the thing develops and progressively generates the final architecture shown here. So this again makes you understand that in fact chemistry is also an information science, because you can program chemical systems. The pieces of the virus are programmed in a molecular program where the information is stored in these pieces, and they interact to get together in a specific fashion. That means the supramolecular operation of the program leads them to the final entity, which is the way in which interaction occurs between the two entities, between the different pieces of this virus, and so that you input information by recognition. The entity then will be growing in order to generate the final entity, and finally, when it is complete, termination occurs, it stops. Now let's go to specific cases. This was just a general presentation of the field put in broad perspective. But I chose, for getting more into the area of nanoscience and nanotechnology, to give examples from assemblies which are constituted by organic molecules, ligand molecules, which are held together by metal ions. These are called metallo-supramolecular architectures, which will have, hopefully, some kind of a function. These metal cations, which bind to the organic molecules and hold them together, they can be said to process the molecular information in the ligand molecules using the coordination algorithm, the way coordination occurs. These are also, in principle, addressable centers, for instance, that one might oxidize or reduce, and you might call that sort of ion dots, like they are quantum dots. So, organization of many entities may lead to the emergence of new properties coming from the way they are arranged. Let's have a look at some of those things. At the very beginning, we started this area by looking at the way in which we can build up double helices. The reason was simply that double helices were, of course, an exciting structure because of DNA. DNA is a double helix. So let me just show you that, in fact, this strand, which contains bipyridine subunits, and this could be the analog of a trinucleotide, interacts with copper-1 and automatically generates a double helix. This is a crystal structure of the double helix obtained. You can make triple helices by taking not copper, but by taking nickel or cobalt or iron with this strand here, which is somewhat different from this one, a little bit modified, and this assembles to give a triple helix. So you see here that by spontaneous but very well directed assembly of these strands plus the metal ions, you get either a double helix or a triple helix. More close to the area of nanoscience and nanotechnology are architectures which look like these grids. If you look at these from a different point of view, you can consider that these grids look like electronic devices. Like you have here sort of solid lines which could be wires, and when they cross over there is a red dot which could be some kind of a semiconductor or something. And this would be the entities which have these slots, 2 or 3 or 4, and the metal ions will locate in here and bring these things together. If the ligand molecule is like seen here, see this and this and this and this and this and this here, then you will bind octahedral ions in these slots. And as you certainly know, an octahedron is 2 sets of 3 points in 2 perpendicular planes in this way, 3 and 3 in 2 perpendicular planes, so that if you connect this part with a metal ion of octahedral coordination, it will arrange 2 such units automatically in a perpendicular fashion. In other words, these ligand molecules, these molecular entities, will be brought together by the metal ions, generating these grids automatically, and only these. Because we have now many entities brought together, this multifunctionality which results from multi-ligand, there are many ligands, multinuclear, there are many of these red dots, many metal cations, multimetallic, maybe one can even make them different. So let's have a look at just some illustration of what properties can be brought about. Let's look at the simplest case, 2 by 2 grids, as shown here, these up here, 2 by 2 grids. They may have new electronic properties. and new magnetic properties. Why not? Let's have a look at some of those. And one can consider that these properties emerge through the multiplicity. They are made possible because we have multiple components in the system. To do a little bit of electrochemistry, this grid built on zinc and 4 zincs and 4 such ligands has redox properties shown by this cyclic voltammogram. What do you expect? You expect that as you introduce electrons, as you reduce the system, introduce electrons, they should go first into the most easily reducible part, which is this pyrimidine here. So if you look at this compound now, you have first a set of 4 electrons, 1, 2, 3, 4. That means you first put an electron in here, then one in here, this 1, 2, then one in here, and one in here, 3, 4. At this stage here, the molecule of this entity now contains 4 electrons. Each ligand contains an electron. Adding another electron is now quite difficult because of Coulombic repulsion between electrons. So you have now to push with the potential by about half a volt, and now you can inject 5, 6, 7, 8. 5, 6, 7, 8. At this stage, the system is now neutral. You have 8 electrons and 8 positive charges. You can, of course, inject more electrons, but then it becomes very difficult. So what I wanted to show here is that this system behaves quite normally. 1, 2, 3, 4, 5, 6, 7, 8. And this is the difference between, in these potentials here, can also be called the Coulombic blockade, where because of Coulombic repulsion, adding a 5th, 6th, 7th, 8th electron becomes more and more difficult compared to 1, 2, 3, 4. What was quite interesting is that when the same experiment of cyclic voltammetry was conducted on cobalt, with the cobalt grid, the behavior was totally different. As you can see here, this reversible cyclic voltammetry curves are almost equally spaced. 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. This indicates clearly that injecting more and more electrons in the system occurs with conjugation between the different ligands. In other words, the system, each electron knows about all the others already present. And this internal communication is provided by the cobalt centers, so that these cobalts in the corners, they provide a conjugation of the ligands. And therefore, as you inject more electrons, each electron feels the ones which are already present. And you have this nice sequence of up to 11 electrons you can introduce into this molecule. Now, the next step was a property which was quite interesting because it was not so predicted. Any coordination chemist would have told you that a unit like bis-terpyridyl iron, this is the iron grid now, should be diamagnetic. However, when you look at the proton NMR spectrum of this unit, you see that it is spread between -20 and +80 ppm. So that cannot be diamagnetic. In other words, it means that this grid has become paramagnetic. Furthermore, when you change the temperature, you see that the spectrum changes dramatically from very expanded, -20 to +80. It coalesces progressively as the temperature is lowered to generate a broad peak in the region here, which is the low spin region. That indicates that at the beginning, the complex was high spin. Some, or maybe more than maybe all of the iron centers have become high spin. And as you lower the temperature, they become low spin, and then congregating here, all the bands merge together in this region. So such a system can have 5 spin states, all the ions low spin and all the ions high spin, and between them 3 spin states with 1 low spin, with 1 high, 3 low, 2 high, 2 low, 3 high, 1 low. And a study done by the group of Philipp Güttlich in Mainz showed that in addition to the change in magnetic state induced by temperature, like shown in the NMR spectrum, one can also induce such changes by pressure or by light. So one has a rather interesting and unusual case where you can induce magnetic spin transition between 3 levels using 3 different triggers. 3 different triggers can be used to change the magnetic state of the system. Now, what I said up to now deals with properties in the bulk solution. What about now looking at an organized entity, that means depositing these units on a surface, so you can perhaps talk to them. If you take, this is now the cobalt grid, you can deposit this cobalt grid on a graphite surface, and here you see the kind of arrangements, rather regular, nice regular arrangements. And if you look more carefully, this is the image which can be obtained by scanning tunneling microscopy, where you see 4 dots, 1, 2, 3, 4, which correspond exactly to 1, 2, 3, 4, the 4 dots of the corresponding to the 4 cations in the structure. If you look now at the current passing through the tip of the microscope, you see that when you pass over one of those centers, cobalt centers, the current increases, conduction increases, meaning that more current flows, and therefore you can look at this as a way to speak, to talk with the cation. You see a large increase in current as you go exactly over these cobalt centers. So this is sort of describing one stage, and of course one can then think of introducing different cations at different places and do a lot of different things, but I haven't time to get into all that. Let's just look at the most complex, the largest of these grid entities we have been making, taking this ligand, which has 1, 2, 3, 4 subunits, treating it with lead. One assembles in one step this very complex grid of 4 times 4 type, where 4 vertical ligands and 4 horizontal ligands are held together by 16 lead atoms. Of course, this occurs in a single operation, but there are multiple steps behind until you end up in generating only this structure. The interest of this structure is not just that it is a complicated structure with 24 components getting together in an organized fashion, but also, if you look at the lead, what can you see? There are 4 identical leads in the corners, they're identical. There are 8 identical leads in the edges, and there are 4 identical leads in the middle. Now, you know perhaps that the nucleus of lead has a spin 1/2, like proton has a spin 1/2, lead has also a spin 1/2, and therefore you can look at it by lead NMR. At 83 megahertz NMR, the lead of lead 207, this is again this reproduction of this disposition of the different leads, and you can see you have green 1, red 2, and blue 1, 1, 2, 1. This is the NMR spectrum. This was measured a long time ago, so it doesn't look so nice. We should probably measure it again, because with the present machines it will look much better. But it shows, interestingly, that by using electromagnetic radiation in the NMR spectrometer, you can separately address these 3 types of lead ions. The type of objects you can generate by this metallo-supramolecular assembly of different components is not limited to grids, of course. Many others can be made. And here I show you just one example of another type, which is a cylinder. You may call that a nanocylinder, which has several levels and several cells. Taking this rigid rod type of unit and connecting it with copper to these other flat units. You see, this is linear, this is flat. You can now connect those together, as you can see here, and generate a cylinder, which is represented on the right here, where you get then 1, 2, 3, 4 levels. There are compartments into which you can then locate different types of counter ions, for instance. But the interesting thing is that you generate a nanocylinder by spontaneous assembly of 3 linear molecules, 4 flat ones, and 12 connector copper 1 ions. This is the crystal structure of this nanocylinder, and you can see very nicely that everything is in place. You have the red ones are the linear molecules, the blue ones are the planar flat molecules, and these golden sort of spheres are the metal cations. Now, I would like to use this to bring you through something which is a bit complicated, but which clearly indicates how one can program these type of systems. I have shown you at the beginning that this type of objects, this type of ligands, give double helices, and have shown you just now that this type give 2 by 2 grids. So if you connect these in the same molecule, what will the molecule do? What can you do? What will the molecule be doing? If you treat such a molecule with 4 equivalents of octahedrally coordinating metal ions, an octahedron is represented here by just a hexagon, and together with 8 copper 1 entities, copper 1, which are also interacting with this ligand. What will happen if you do that? You can realize immediately that the 4 octahedral coordinations will make a grid in the middle. Indeed, they make a grid in the middle, and they have 4 corners, which each of them is continued in a double helical fashion, double helix. Now, if you change your way of reading this molecular information, you can think of using pentacoordination. That means copper 2. Copper 2 is pentacoordinated. How can you make pentacoordination? By taking 1 by bis coordination and 1 tris coordination, so that this should connect, a pentacoordinated ion should connect 1 unit like this with 1 subunit like this. And in addition, you add 4 copper 1 ions and you get this. This is now a very highly entangled, very complicated structure where molecules wrap around each other in a very specific way. And you see that the end of one molecule, which is here, is connected to the center of the other one. The end of one, for instance, this unit, is connected to the center of the other one, for instance, this unit. And they go around the circle in this way, showing that depending on how you look, how you read the molecular information, you get a different object. This can be called the multiple expression of molecular information here. And you can see that with a single program, you have several outputs. And this is a very interesting feature where the same molecular information generates different outputs. This is the crystal structure, just to convince you that this has indeed been obtained, which is a very complicated object with highly entangled molecules. The best is, of course, to have a crystal structure. It happens that this compound crystallized quite well. And here it is. That's the crystal structure you see here with the red ligand, the blue ligand, the green ligand, and the yellow ligand. The other one, the one which was here on the left-hand side, we don't have the crystal structure. It didn't crystallize well enough, and so we only can rely on normal spectroscopic methods, but they all are in favor of this type of structure. Now, let me just note that, in fact, I have up to now written these ligands in this way. And any coordination chemist would write the ligands in this way because this presents a nice site for binding a metal ion to the 3 nitrogens. But this is not the correct shape of the free ligand. It is not. What is the correct shape? These nitrogens here do not want to look at each other. They want to turn in a transoid fashion, as shown here. So these shapes, the way they are represented, this shape is not correct. These shapes are not correct. One should turn around each of these carbon-carbon bonds and orient these pyridines in this way. If you do that, something interesting happens. You induce a helical folding of the molecular strands. That means you just take this and you now draw it with your pencil, your pen, in the correct fashion. That means with turning around each of these bonds, and you end up with a helix, a helical molecular strand shown here. That is the crystal structure, the solid state structure of this entity. In other words, quite interestingly, this type of sequences, pyridine, pyridine, pyrimidine, pyridine, pyrimidine, pyridine, pyrimidine, and so on, leads automatically to the folding of the chain. And we have developed this quite a lot. And you can define what you can call a folding codon, meaning that depending on the sequence of heterocycles, you obtain a different shape of the resulting type of molecule. In terms of properties, something interesting occurs. Just to mention one, which can be interesting. As long as the chain does not overlap, you have a normal fluorescence emission. But as soon as the chain overlaps, as shown here in this 2 turns helix, a new band appears, which was an excimer band due to the overlapping of the conjugated pyridine units in this structure. Let me note. Now, in the grids, these chains are extended as shown here. When they are free, they are helical. So what happens? What can you do? You can realize then that in the open form, there is a bend in the molecule. And when you bind metal ions to these molecules, these bonds turn around here, this and this turns around, and generates then this new shape. And now you have this an extended form. So this is bent, as you can see, and this is extended. Conversely, one can also imagine a sequence of pyridines, which, when you oppose the nitrogen's direction, is necessarily a linear molecule. Then, when you bind a metal ion, this should turn around and give a curved molecule, a bent molecule. So by these 2 ways, here you can go from a helix to a band, to a linear, and here you have to go from a helix, from a linear band to a helix. Can we see that? Indeed, and I haven't time to get into details. Let's look at the first case. This is the molecular model of one of those helices. It's about 11 angstroms long. And when you add lead ions, they bind to these subunits, to these sites here, as shown here. The leads are bound to these sites and extend the molecule. So you have an unfolding by ion binding. An interesting process you can then imagine is to try to reversibly modulate extension and contraction. If you add a binding agent, this was in fact our first cryptand we made many years ago, 1967, 68. This ligand, this cryptand, will bind lead and remove it, so that this compound now, in this case, is helical. This is helical. If you then protonate the bridgeheads here, the lead goes out of the cavity and binds again to the molecule which is outside. If you then add base will here generate deprotonate these protons, generate the free ligand, and then lead will automatically go back, will be picked up again, and so this linear strand will go back to the helical. So you can reversibly, by adding acid and then adding base, going back and forth, and have a sort of an extension contraction motion based, fueled by acid-base neutralization energy. This is represented here: helix, strand, extended strand, helix, strand, and so on and so on and so on. I said that in addition to taking a helix, unfolding it by metal binding, and then folding it back by removing the metal, one can also start with a linear strand. I have not time to get into that. Fold it to bind around metal ions and unfold it by removing the metal. This can be called nanomechanical devices. They are small entities which generate molecular motion of extension contraction type, which is also present in the biological molecules, and it's a sort of a controlled motion between these organized structures, and they can be called motional dynamic devices. To bring together the first description of metallo-supramolecular architectures, the grids, and this one can see that there is an interesting consequence for nanoscience and nanotechnology. What is it? Right now, you know that all the very advanced devices made to build up computers and all these fantastic objects we use, like this video link we have between Cali and Strasbourg, this is made possible thanks to the very advanced technology we have. And this advanced technology is all based on fabrication of these complex devices. This is very powerful. We know that because it works. We know that it works. It works very well. However, there may be another approach of interest, which is to say, yes, one way is to fabricate, but there's another way which would be interesting, which is to say, let the structure build itself up. If you design the correct components, and if you put into operation the correct connections, then maybe you can let the object build itself up spontaneously, but in a controlled fashion. That means going from fabrication, the need to make, to self-fabrication, to let the object build itself up. And that, of course, would be the ultimate fabrication. I consider that that is a very interesting approach to nanoscience and nanotechnology, which for the moment is not, of course, far from the realization of the technologies we know of, but which nevertheless is a very important one to consider in the future. This part of my talk has concerned designing systems as accurately as possible, putting information in the system, programming it so it will generate the final self-organized entity. There's another approach I would like to mention for the end of my lecture, which is to see if we can build up systems which are able to select the components they need in order to build themselves up. How can this be done? You need, of course, diversity. You need many different bricks, and you need dynamics. You need to have interactions which are reversible, because you want these interactions to be weak enough so as to allow the system to get into thermodynamic equilibrium and look for the best arrangement. This also leads to the possibility of adaptation. If a system is able to select, it will perhaps also respond to external types of interactions, of solicitations, of stimuli. So, if you think back over supramolecular chemistry, you realize that the components are in supramolecular entities, the components are held together by interactions which are rather weak, which are rather labile, which are reversible. A supramolecular object can break apart and reform itself reversibly. This makes, of course, possible adaptation by changing constitution in principle. You can then try to transfer this ability of falling into pieces and reconstituting itself into molecular chemistry, importing dynamics, this type of dynamics into molecular chemistry by introducing reversible covalent bonds. I'll come back to that, it will become clearer in a moment. If you build molecules which contain reversible covalent bonds, these molecules should also have the ability to dissociate and reassociate, to fall into pieces and to reconstitute themselves. And bringing together the supramolecular part as well as the molecular part, one can call this field a constitutional dynamic chemistry, a chemistry which is dynamic in the constitution of its objects of either molecular or supramolecular nature. I would like to stress that this dynamic chemistry is quite different from what one usually calls dynamic chemistry. In chemical physics, reaction dynamics are concerned, or in physical chemistry, reaction dynamics are concerned with the rates and mechanisms of reactions, the elementary steps, all what happens when a reaction occurs. Motional dynamics are motions in molecules. You have just seen some, but of course there are more complicated ones, and there's a vast field, a broad field, which is being developed, which concerns molecules which might act like motors or like machines. Constitutional dynamics is quite different. Constitutional dynamics deals with reversible changes in constitution. You want to change the constitution of the object by introducing new components or by removing some components. What can this bring? Such chemistry can, first of all, will generate diversity, either supramolecular or molecular. If you have diversity, you can, of course, operate selection, because you can choose the component which may be the best one for a given condition, for given conditions. That is of interest for biologically active substances. I will not mention that much, just a little bit to give you some idea. Have dynamic nanostructures and dynamic materials. I will give some examples of these here, just to give you an idea of how this field has developed in the last 10 to 12 years. First of all, what about biologically active substances? You certainly know that when you make a drug, a pharmaceutical compound, which is supposed to have a biological activity, you want, in Emil Fischer's terms, you want to make a key for a biological lock. Either you try to design this key and make just one key, the correct one, but this can be very difficult because you may not know how the lock is looking, what is the shape of the lock, so it's difficult to design a key. So this may be of course, very satisfactory, because if you can do it, you understand what's going on, but it may be too difficult and too long, take too long. Combinatorial chemistry is another approach which says we make many different keys. We try all of them, and we are lucky. If we are lucky, one will fit, will be good. Nowadays, in companies, one has high throughput screening, fast robotics, and as a consequence, one can then can certainly generate many keys and try all of them, very many, maybe 100,000 per day, and see if one is lucky, one will be active. But this is not very satisfactory in terms of understanding what's going on. So what you can do is the following: combine the power of combinatorics with the power of recognition. In that way, you make just fragments of the keys. You don't make the keys, you only have fragments, but you build them in such a way that they can reversibly bind together and generate all the possible combinations resulting from these components. So because you have now fragments which can reversibly connect, you have access to the full set of all the keys resulting from all the combinations. So if you now add to this the lock, the biological receptor, it will of course bind best the key which fits best. And this is just the law of mass action, the law of Le Chatelier, which certainly you have heard about and you must have seen in your lectures, where I may have even used it, where the best binder is selected and amplified, And so you can say that it's the lock itself which assembles the best key. This is, of course, a very attractive approach where selection from a dynamic combinatorial library leads to the assembly, which is the best one, and where you can then hopefully identify this key, and then you have a substance which binds strongly to a biological entity, to a given receptor site, like this shown here. Now, I haven't time to get into that. It's, of course, a case of molecular recognition-driven component selection. I have no time to go further into it. I wanted just to show you that this is a possible approach. Let's now have a look at dynamic materials. What about dynamic materials? These materials are materials where, for instance, polymeric ones, where the monomer components of the polymer they can be supramolecular or molecular, and they can then lead to a reversible component exchange. Also, analogs of biopolymers may be considered. I have no time to get into that. I will just show you a few slides which relate to dynamic polymers, which we call dynamers. These are polymers which are built on components which can reversibly associate. Let's first look at supramolecular polymers of this type. This many years ago, in 1990, we have studied these, but this is the case which opened the field of supramolecular polymers. Taking this component, where you can see here in the middle, a unit derived from tartaric acid. This is a tartaric acid unit, where the two OH, you know that in tartaric acid there are two alcohol functions which has been transformed by an ether connection with the attachment of C12H25 chain here, which can be attached here. The two carboxyl groups of tartaric acid have been modified by attaching recognition sites here. This is a recognition site which is a donor-acceptor-donor hydrogen bond. You can do the same thing, same spacer in the middle, but now at the end you have a unit derived from uracil, which have acceptor, donor, acceptor. And you realize easily that donor, acceptor, donor, DAD is complementary with ADA. So when you mix those, you will get hydrogen bonding between DAD and ADA, ADA, DND, and so on, leading to the formation of a long chain, a supramolecular chain of polymeric nature. Just to indicate that new properties will appear, this is a solid, that's a solid, and this is a liquid crystal. So new properties appear, and indicating that indeed you obtain a new entity. It happens that this is a liquid crystal with a very very broad range of liquid crystallinity. It also indicates one thing which is important in self-organization. Let's analyze the formation of this system. It is a self-assembly which happens in a hierarchical fashion in steps. You first have two molecular components, this one and this one. They assemble into a supramolecular polymeric chain. When you study this chain, the objects they form by X-ray scattering, you get as a result, this was done with a physics laboratory in Paris, you find out that these chains form a triple helical strand by wrapping around the axis of a cylinder, and the C12H25 chains, which are attached to these OH groups of this tartaric acid, they stick out. So they can stick also together and then come to the formation of fibrils, as shown here, where these units here, if you see that, I guess you can see it on the screen, I hope. This thing here is part of these fibers here, and they can then attach to one another, these fibers, by entangling of the side chain, leading to the formation of these fibers. So you have three steps from the components making the polymeric chain, supramolecular polymeric chain, from this making the triple helix, and from this making the fibers. Now, if you want to look into dynamic covalent objects, we have first to try to find a reversible reaction of interest. Of course, all of you know that an amine can condense with a carbonyl to give an imine, and this is reversible. Water is eliminated, and that can attach again and go back here. You can do the same with hydrozides, CONH, you can react with this carbonyl, and you get this acyl hydrazone. Can we use this kind of reversible reactions for a given purpose? You may say it is maybe not very interesting to make materials which can fall apart, which can dissociate. It might not be of much use. But this is not really the point. In fact, they bring new properties. So if you look at what you may call covalent dynamers, that means polymers of covalent nature, but which are linked together by reversible covalent bonds, we can think of condensing a diamine with a dialdehyde or dicarbonyl to make a polyimine, or condensing a dialdehyde with a dihydrazide, CONH, to make a polyacyl hydrazone. So these are polymeric entities, these are polymers, which contain cleavable, reversible imine bonds, C double bond N. So let's look at what one can, I don't want to get into details, but I want to illustrate to you what type of new properties appear because of this dynamic character. What about mechanics? What about the mechanical properties? If you use this compound, which this is a polymer, which has been made from one component, which contains dimethylsiloxane units, and this is the NH2 component, and another component, the aldehyde component, which also contains these silicones. You mix those two together and you get this chain, which is represented here. Now this chain is a very soft and very stretchy type of film. It forms a film which is mechanically a very bad film. It is mechanically very soft, very stretchy, very floppy, not interesting. But then you can think of taking a set of hard monomers, not so flexible as these ones. This has a phenyl ring, not so flexible, not flexible at all. And this has some flexible chain, but it's not so flexible as the silicones, as the dimethylsiloxanes. So if you take this and add it to this, then you will get a chain where you introduce these units into the new chain, and now these more rigid components will enter into the chain progressively as you add more and more of it. With 25% of these hard monomers, you see that the film now looks already much better. Not so soft, not so stretchy anymore. With 50%, it is now mechanically strong enough not to bend anymore over its weight. I mean, 75, you still keep flexibility, but you have also this possibility of having the flexibility is still there, but it is more resistant, stronger film. So you can progressively convert a soft and stretchy film, this one on the left, progressively into a more and more strong, tough film as you introduce more of that. And that is made possible because of the reversibility of these bonds, so that these units here, the hard monomers, can enter into the chain and modify its mechanical properties. What about optical properties? It would be nice to have materials whose optical properties can change as a function of other components you are adding to it. Let's have a look. We look at a film which is colorless, formed by AB, two components, A reacting with B. And another film which is perhaps a little colored, a little bit of color, A prime, B prime. You superimpose them, and at the interface where they are superimposed, you should now be able to generate the combination of A with B prime and of B with A prime. A will combine with B prime, and B will combine with A prime. And if this new combination is colored, you will see it. It may also be fluorescent, and you will see it. So at the interface, only where these films are superposed, there will be changes appearing. And if one, I repeat, of these new combinations has a color or a fluorescence, you will see it. So this was done in this way by Japanese co-workers. You have a nice cat here, which has the head and the ears. That is the polymer AB. You have the mustache here, the eyes, and the inside of the ears. That's polymer A prime, B prime. You see that they are superimposed here. So now you heat and you see color appears and fluorescence appears, only where they are superimposed. This, of course, is something which, first of all, indicates that indeed this recombination works at the interface. It also shows that if you have such a superposition of films, you can perhaps write with a heating laser at the interface. And if you superimpose a stack of those films, you can even write in 3 dimensions in principle. So you have optical material which is responsive to external stimuli, in this case, simply temperature. And you can then make these drawings. You can do a number of things, and probably, I hope in the future, this type of properties of dynamic films can be used. The last example of this would be to see if you can make films which will heal, which will repair themselves. Take this film, which has been obtained by a reversible Diels-Alder reaction. I don't want to get into it, but it's a reversible reaction which is fully reversible at room temperature. I want just to illustrate that when you take a film made from these objects, which continuously dissociate and reassociate, you can cut it in 2 and superimpose the 2 halves. You see here, and now you press it and heat somewhat, and you can now pull on it and it sticks again. That means that at the interface between the 2 films, you have now resealed, repaired the cutting, and you have new chemical bonds have formed, so that the sticking together is not a physical sticking, it's a chemical recombination of bonds. Let me finish by a short section on going a step further, adaptation. I had told you that if you can select, then the system can perhaps change its constitution, vary its constitution in response to different triggers, like the environment, the medium, a change in phase, a change in physical factor like pressure or temperature, a change in chemical effector like protons or different solvents or metal cations, and even a shape change. So these nanostructures would be adaptive. They would adapt to these changes, and that of course can be quite interesting, because if you can make nanostructures by self-assembly, that is one thing, but if you can make them in such a way that they are responsive to different stimuli, they will be able to adapt to changes in stimuli. First, a very simple case, and you may consider this as trivial. It is not so trivial. When you have a mixture and you crystallize the components in that mixture, you want simply to purify. When you have a mixture, you hope that one component will crystallize and the others remain in solution. That's the normal crystallization. However, when what is in solution is dynamically interconverting, then the situation is very different. Take this ligand here, treat it with copper-1, and you find by nuclear magnetic resonance that you have in solution a mixture of equilibrating, and insist, a mixture of equilibrating species, a helicate, double helix, a triangle, and a grid. Okay? Now, if you crystallize this, if you put it in conditions of crystallization, the solid contains only the helicate. But since all of those are in equilibrium, when the helicate crystallizes, these transform into helicate, so that at the end of the crystallization, there's nothing left in solution. It's not like a normal crystallization, where the crystal, what crystallizes is one compound, and all the others remain in solution. Here, what crystallizes is one compound, but all the ones in solution transform into this one. In other words, the solid, the network of solid, the forces of the solid network have driven the system to generate only one entity because the solid packing has selected this structure. Another example of this adaptive self-assembly is that when you take now this ligand, treat it with copper-2, when you operate in nitromethane, you get a square. When you operate in acetonitrile, you get a hexagon. What is the reason for that? Nitromethane is a bad coordinating solvent. It does not coordinate well. Copper-2 would like to be pentacoordinate. I already mentioned that earlier. But in nitromethane, it's a bad solvent, so it cannot coordinate. And so it just does what it can by itself, and it forms this unhappy grid 2 by 2. But that's what is the best in this solvent. If you go to acetonitrile, acetonitrile has a nitrogen which is a much better coordinating center. So this forces the system to generate a unit where the acetonitrile can coordinate. That means it opens up, generates a hexagon, and is this rather large hexagon, as shown by the crystal structure shown here, acetonitrile molecules connect to the coppers. You see here, acetonitrile molecules connected to copper inside the cavity, as shown here. So that is a case where the different solvents induce a different assembly. And indeed, when you add acetonitrile to this solution, you go progressively over from the grid 2 by 2 to the hexagon. Finally, the last case is the following. It's again coming back to the grids and just showing how grids can be obtained by this adaptive self-assembly. Take this dialdehyde here, which has a pyrimidine unit with 2 nitrogens. And take that aminophenol, it has an SO3 minus group to be soluble in water, and this NH2 can condense with this carbonyl, and the OH can be a center of coordination. So when you mix these together, before you add any metal ion, they will connect and make monoimines. That means there will be some non-connected, some will form a monoimine, and some will form a bisimine on each side. The ligand which results from the formation of the bisimine is represented in red here. This red unit here is this ligand which results from the condensation of 2 units of this with 1 unit of this type. Now, before you add metal ions, this is a complicated mixture. As soon as you add copper-2 or zinc-2, you obtain only one entity, the correct grid, where you assemble 8 such units into 4 ligands, which then self-assemble into the grid. In other words, you have here, again, several different steps. First step, you condense this amine with this carbonyl. That then generates a ligand, and these ligands then assemble into the grid. Of course, along the way, a lot of complex things can happen. You can have monoamines which bind the middle, and then they bind this other unit, and so on and so on. But at the end of it, this is what you obtain. So that assembly can now be put to use in the following way for selection. Suppose you mix this aldehyde, this methyl ketone, and this dialdehyde there are 3 such, with 1, 2, 3, 4, 5 different types of amines. This amine, this one, this one, this one, and this one. When you mix those together, you get a complicated mixture of exchanging imines. Very complicated because, as you can see, one of those amines can condense with this carbonyl, or with this one, or with this one, or this one can condense here, and the other one can condense here. So a very complicated mixture. You cannot, and it's difficult to analyze. But as soon as you add the metal ions, here, manganese, or iron, or cobalt, or nickel, or zinc, or copper, or zinc, you obtain only one entity. This grid, which is the one we have seen here, same grid. This grid is generated automatically from this complex dynamic library by correct selection. That means that in this at the end here, you have in solution all the entities which do not form the grid, and in the grid only these two entities, the ones which have a frame, a black frame or a blue frame. That is, in some respects, a good example and quite impressive, because it's a good example of how the formation of an organized structure can lead to the selection of the correct components needed to make that structure. Of course, you can in principle extend that to many other cases, but I don't want to go further into it. I think that's a good illustration by which you can see that nano objects can be formed by self-assembly, but not only by self-assembly with just the correct components, but even selecting their components. Of course, you could say that maybe if you change the conditions, you will assemble something differently. So let's conclude. This constitutional dynamic chemistry I just presented to you deals with systems which undergo continuous recomposition, recombination, reorganization, and so on. They can respond to pressures. That means, when I mean pressure, I mean they can respond to factors which are either external or internal. I only showed external, and they change their constitution by selecting the correct components. This concept of selection is a very important one, and I think in the future it will be of more and more importance in chemistry also. That makes possible adaptation, devising adaptive systems, adaptive materials and technologies, and for the topic of your today's symposium, also adaptive nanostructures and adaptive nanotechnologies. Just to make a point, we are talking here about nanoscience and nanotechnology, but this means that people are looking especially for objects of small size, nano size. But as you know, this is not the important thing. The size is, of course, important because it makes possible putting more and more objects into the same volume. However, the goal is really to have complex entities, to have entities where the complexity is high enough to generate very interesting functions. So that, you know that the very famous physicist Richard Feynman said he has a sentence quoted a lot: there is plenty of room at the bottom. You understand, of course, that means if you make objects smaller and smaller, you can accumulate more and more of them in the same volume at small size. But this is not really the goal. The goal is really complexity, and so you can really claim that there's even more room at the top than at the bottom. So let me come back to the theme from the beginning. Self-organization is the driving force which makes matter complex. Molecular chemistry is the basis. Without molecular chemistry, there is no other chemistry. That's the basis. This then leads to understanding what happens between molecules, supramolecular chemistry, designing the systems. Then you realize that supramolecular chemistry, in fact, is dynamic, and you try to introduce these dynamics into molecular chemistry by introducing covalent bonds, so that you can now develop a chemistry which is dynamic in its constitution. This allows selection and therefore makes possible adaptive chemistry. So we can see a large part of chemistry more and more evolving towards adaptive chemistry, evolutive chemistry, and why not, you may call it Darwinian chemistry, realizing, of course, that it is still very far from biological evolution, but progressively chemistry will become more and more adaptive, evolutive, and generate systems which can respond and can progressively become self-organized at higher and higher levels of complexity. So that's what I wanted to tell you today. I thank you for being around, for being here at this meeting. I'm happy to see all of you. It's a bit far away, but nevertheless, thanks to these modern technologies, we can nevertheless talk to each other and see each other. So if you have questions, I can answer some questions, but this will be depending on the time you have, and we can just do whatever you want. Manuel, thank you. It's nice to be able to talk.
Thank you very much, Professor. ¿Alguien tiene alguna pregunta para el profesor Lehn? No questions?
Professor Lehn, thank you very much for this very excellent talk. I wanted to ask you about the elastomers. I suppose you were trying to get thermoplastic elastomers, mixing the siloxanes with and mixing the hard part. Now you changed the siloxanes to the, I think it was
some things with fin rings and so on, yeah.
Yeah, and don't you have to have in consideration the glass transition temperature of the soft segment in order to get, for example, a thermoplastic elastomer that can be used in a wide range of temperatures?
Sure. I think you are, of course, totally right. You know, this was, at this stage, we are not polymer chemists, and of course, we realized that at this stage, the only thing we wanted to show is that because these polymers are dynamic, we can modify their properties. Now, I think people who are really polymer chemists and who are interested in a specific property, they should then try to use these properties. The polymers we made are thermoplastic. We had no goal. We didn't want to make a polymer which can be of commercial use. Obviously, the polymer you have seen, these films, are of no commercial interest. They are colored, they are floppy, they have a lot of problems. But the important thing was to show that there are new features which appear because they are dynamic.
Thank you very much.
Is there any other question? He's asking why for these self-assembles are used only first row metal transition metals.
Very good question. Yeah, this is the reason is you are a coordination chemist, so you certainly know that if you use second row transition metals, the connections are very strong and they're not dynamic anymore. If you use, we have used ruthenium and rhodium, and in fact ruthenium and osmium in some cases. Then the binding of the ligands is very, very strong, and they do not dissociate. So you cannot use ruthenium and rhodium in systems which you want to be dynamic. But in other work we had done earlier, we have also used ruthenium and rhodium and things like that. But these are too stable, too strong. This is why we use first row transitions. Also, in terms of application, if one can get something with first row, it's much cheaper, as you know, than the second row transitions. And that's also perhaps later on a consideration.
Okay. Another question?
Yes, I want to thanks Professor for being with us. So the question is, what is the role of the P stacking interaction in this self-assembly?
These are important. I did not insist on what interactions, but for instance, in the helix, which I showed, obviously the main force is the fact that these nitrogens are in transoid position, but they are also stacking. And so in a number of, in fact, I didn't show much of that, but there are quite a few cases I could have shown where stacking interactions are quite important. We have a case of a polymer. In fact, Manuel knows about that because it was at that time an American postdoc, Franz Vollmer Anderson. I think Manuel must have known him, I guess. And he studied a system where the driving force was stacking interaction in hydrophobic effects and stacking interactions. So they are very important. It depends, of course, on the surface in contact, but they are there.
Thanks.
First of all, thank you very much, Doctor. It's really an honor to be able to talk to you. I'm just curious about one aspect. I would like to know in what grade quantum mechanical effects are relevant in supramolecular chemistry.
What effects are available?
Quantum mechanical effects, are they relevant?
Quantum mechanical effects. Yeah, that's a point. Yeah, I understand. We have not worried about that, I must say. I guess there must be some quantum mechanical effects, but I guess, we could compute things. Of course, one can compute it by simple molecular mechanics, which is not very satisfactory for if you are a quantum physicist or something. But there might be interesting points. For instance, I could see that if you use metal ions like gold metal ions, then the coordination can be interesting and maybe interesting effects can be brought about. But you are quite right. On the nano size, there could be some quantum mechanical effects. We have not looked in it, and I suppose that in the structures we have made, they don't play right. No, but wait a minute. Depends what you call quantum mechanical. Obviously, the conduction which you have in the grids, which I showed you, and the way in which the electrons communicate with one another in this electrochemical reduction, these can be considered as quantum mechanical effects, but not really. I mean, they are simple physical chemical effects. We have not really worried about quantum mechanical effects like things which could be due to the appearance of new properties, which depend on size and which make the objects different. All the components we have used behave more or less the way you expect them to behave in coordination chemistry.
Question? If not, let's say thank you again to Professor Lehn.
So I see you have a nice room there, huh? It's quite a nice room.
Yeah, it's very good actually.
And a nice audience. So what is coming up now? You have now lunchtime or what?
Yes, we had a lunchtime, and then after 2:30 p.m. we are going to have a poster session, and then last talk at 4 p.m. So we have here people mostly from the chemistry department, I guess, right? And it's a mixture of undergrad students and graduate students and professors from the chemistry department mainly. So,
Hello everybody. Is Professor Abruña around also?
no, he wasn't able to come to the city.
He wasn't able to come.
Yeah.
Mm-hmm. And the other speaker,
At the end, the other speaker is Professor Carlos Arango. He is from University,
okay.
and he's actually graduated from Cornell University too. So.
Okay, very good. All right. So, what is the weather there?
It's very hot actually right now.
Warm.
Very hot. Here it's cold.
I guess
What is the temperature? What temperature do you have?
25 degrees.
around 25.
5.
It's too much, right?
Oh, come on. Here it's 10. All right. I think we should
When
come
are you
over
coming
there.
to
Yes.
visit us? Professor Lehn?
Yeah. I guess that's a good time in the year. I think this 35 is somewhat too hot. I would prefer it a bit cooler.
Yeah.
Well, the problem, we are in the tropic, and the temperature is almost the same all year long.
Okay, you have 35 all year long.
No, 25.
25.
Or 25.
Yes.
Oh, right now it's 25, not 35.
Yes,
No.
25.
20.
Okay, I forgot. Okay, 25 is nice. That's a nice temperature. That's a good place. That's a good place.
Yes.
Okay, so enjoy the rest of the day. And I was happy to be able to talk with you. I wish you a lot of success in the future. And as soon as it's possible, I will come around. I don't know when, but sometime. And Manuel will keep in touch, I suppose.
Yes, sure.
Okay.
Okay.
Thank you very much.
Professor. Say hi
It
to
has
the rest
worked
of the
very
group.
well. I'm very happy with the way it worked. It worked very well.
Thank you.
And furthermore, you see, when you do that, you can sit during your talk, which is less tiring than when you stand up.
Sure.
Okay, thank you.
Okay. Good. Have a good day. Bye-bye, everybody.
Thank you. Bye-bye.
Bye-bye, everybody.
Thank you. Por favor, recuerden que a las 2:30 tendremos la sección de pósters y a las 4 la conferencia de Carlos Arango aquí en este mismo lugar.